Hi folks, welcome to this video where we recap some applications of derivatives and maybe introduce one other one. So in economics, the most basic derivatives describe dollars per item, either cost, revenue, or profit. If C of x is a function for the cost of producing x items, then dc by dx is measured in, well, let's see, cost would be, let's assume we're talking about dollars here, though I realize that's wildly culturally specific, so whatever monetary value you want to choose, over items. It's dollars per item, or it's euros per item, or it's rubles per item, or whatever. It's the rate of change of cost with respect to the number of items produced. It also provides an estimate of producing the A plus 1th, or the next item. It can be used to estimate the true difference in cost between making A plus 1 items and A items. The same idea applies for revenue and profit functions. So revenue is money that's coming in. Profit is the difference between revenue and cost. So right over here, if you ever need profit, just money in minus money out. The example that I'm going to do, I actually have another video on it where I do it in sort of greater detail if you really want to dig down on what's happening graphically here. But I think we can get through this and get a good idea of what's happening without getting too bogged down. So I'll try and keep it going at a decent pace. But if you want a more sort of in-depth look at this, though not a super in-depth look at economic derivatives, you can check out the video description and there will be a link there. So let's say that we wanted to make I Love Math SL1 t-shirts, and the cost for producing X shirts is this function for whatever contrived reasons. Because we got to pay $2,200 for use of the warehouse and machinery, and then we have some fixed costs for the t-shirts, and maybe some variable costs for like the health benefits of our employees, and so on. We want to find the cost of producing 150 shirts. Well, that just means subbing 150 into this function. And I don't want to go through typing in numbers here. That's going to give us 34, 33, 75. You can pause and try it on a calculator. Find the cost of the average shirt if 150 are produced. Well, the average cost will be the cost of making 150 over the number that we produce. Now, you could get into a little argument here over whether the 2200 matters. I think it does. So if we do this, we would have 34, 33, 75. That's the cost of making 150 t-shirts. And then we just spread that out between the 150 t-shirts. And again, you can type that into your calculator. You'll get that it's $22.89, the average cost. Pretty high. If we made more t-shirts, maybe that average cost would come down. Maybe it wouldn't. I don't know. But it might be something that we'd be interested in if we want to optimize our business model. So the cost of producing 151 shirts, we could figure that out. Put in 151, and we'll get 34.48 and 19 cents. This is rounding to the nearest penny. So then it asks us, what's the true cost of producing a 151st shirt? And to find that out, all we have to do is take the cost of making 151 and subtract the cost of making 150. So making 151 shirts cost us $3,448.19. Making 150 shirts cost us $3,433.75. So that 151st shirt cost $14.44. Less than the average cost to this point. So making more shirts at this point seems to be bringing the average cost down. That's nice to know. So we should probably consider making more of them, assuming that the demand is there. And of course, the demand for Math SL1 t-shirts is like super high. Every day. Just get bombarded with emails about this. I do not. Okay, we want to find C prime of x. We want to make this calculus E. So C prime of x is not that hard to find. It's going to be 39x squared plus 0.04x plus 5, for whatever that means. That's the rate of change of cost at any moment, or at any point, at any x value, number of items. F asks us to find C prime at 150. And again, this is just putting numbers in a function. So if you do that, if you put 150 into this C prime function, you're going to get 1438, which is really close to our answer in D. And if we want to interpret it, I mean, what it really is the rate of change of cost when 150 shirts are produced. It's a bit abstract, though, but that rate of change of cost is going to be constantly in flux. The other thing it does really well, though, is estimate the cost of producing the next, or the 151st shirt. You can see that that $14.44, the $14.38 are really similar numbers. And it's actually easier to plug into the derivative than to find what the actual cost of the 151st shirt is. If you want to see this exact example done in more detail, again, there's a link in the video description. But the big idea here is that C prime at A provides an estimate of the cost of producing the next item. One thing that last example illustrated is that the Leibniz notation helps us understand the meaning for derivatives. So when I write dc by dx, I know that the derivative is going to be measured in whatever this unit is over whatever this unit is, the x unit. Another way that you can think about that is just imagining the axes. So if I have cost here, and I have items here, well, slope is going to be delta y over delta x. So it's going to be y's over x, or dollars per item, or euros per item, or whatever currency you want to use. We're often confronted with two different types of rates of change. We can talk about average rates of change, and average rates of change really are not about calculus necessarily. It's just going to be the slope of the secant, which cuts a function in two places, or delta y over delta x, or y2 minus y1 over x2 minus x1. If you want to do that in function notation, it's typically f of b minus f of a, where b is the final sort of point, over b minus a. Okay, those things all essentially mean the same thing. Instantaneous rate of change, on the other hand, is what calculus does. It finds the slope at a point, or the tangent slope at a point. So we're going to look at this in the context of one problem that's going to have both average and instantaneous rates of change involved. And I wrote it out here in sort of my own chicken scrawl because I made a goof in the notes. They should be fixed up, though, for the downloadable version. The temperature of water in a pool after n days is modeled by this function. So n is days, T is temperature in Celsius. Find the average rate of change. Okay, so that means we're going to need rate of change, the temperature at day 20 minus the temperature at day 0 over 20 minus 0. Off to the side, we're going to need to find T of 0 and T of 20. So T of 0 is going to be 15 plus 10 times e to the negative 0 over 5. E to the 0 is just 1, so the initial temperature is 25 degrees Celsius. T at 20 is going to be a little more challenging to find, so it's going to be e to the negative 20 over 5. Probably need to head to the GDC. I type in 15 plus 10 e to the power of negative, I'll use my fraction button here, alpha y equals 20 over 5, and I probably should have just divided 20 by 5 myself and called it negative 4. And I write it down, I get 15.18 roughly. So that's the temperature after 20 days. So it fell almost 10 degrees in 20 days. I expect the average rate of change to be negative because it went down, and to be about half a degree a day. Let's put it in here. So we have T of 20 is 15.18. T of 0 is 25, all over 20 minus 0, which is just 20, and back to the GDC. Once again, I'm going to use the fraction button. And this time I'm going to use that answer that's already there. And I'll just say that minus 25 over 20. That way I keep all the decimal places. I get negative 0.491. Seems reasonable. And the units here are in degrees over days. So degrees per day. Let's give that some meaning. On average, the temperature decreased at a rate of 0.491 degrees Celsius per day over those 20 days. Now let's deal with the calculus side of things. T of n is 15 plus 10 times e to the negative n over 5. So that means the same as 15 plus 10 e to the negative 1/5 times n, if you want to think of it that way. When we differentiate, that 15 goes to 0. The 10 e to the negative n over 5 stays, times the derivative, which would be negative 1/5. So what we get is this. T prime of n is negative 2 e to the n over 5. The last thing it asks us is to find the instantaneous rate of change on day 20. So instantaneous lets us know that we're talking about t prime. So this is t prime at 20. One way that we could do this is to put in 20 over here into t prime. Let's see what we get. Negative 2 e to the negative 20 over 5. Again, that's just negative 4. We get this, negative 0.0366. What that tells us is that on day 20, or exactly when n equals 20, the temperature is decreasing at a rate of 0.0366 degrees Celsius per day. Now, why would there be such a big disparity? Well, we already know this because of the nature of exponential functions. They decrease quickly at the start or around where x is equal to 0, and they're going to decrease less quickly when we get to further and further out because they're asymptotic in nature. One other way that we could have answered part C is by not relying on part B. Instead, I could type in the original function here. So 15 plus 10 e to the power of negative, and again I'm going to use my fraction button, x over 5. And I'm going to quit here, and I'm going to use math. And I go down to n derivative. This is not the only place you could find it, but I want to find the derivative of that function I just put in y1, so I'll press alpha y1. And I want to find it when x is 20. And it will just work it out for me. Alternately, I could have gone to the graph of y1 and found its derivative there. But I might have had to mess around with window settings. So I'll go second, trace. I choose number 6, which is dy by dx. And I tell it that the y value I'm interested, or the x value I'm interested in is 20. Okay? And again, it tells me negative 0.366. So there are 3 ways of finding that derivative. If you have your GDC, which you probably would for this question, I think there's a lot to be said for using the last kind of technique where you don't have to rely on your answer from part B. There are some practice questions on page 555. I hope this has been helpful. Good luck with the material, and take care, folks.